Welcome to Hartman Math. Today we're going to take a look at polynomial and synthetic division. Prior to that, we have a warm-up looking at some quadratic functions. Go ahead and pause the video here. Work through numbers 1, 2, and 3. Number 1, what we should have gotten when we say minimum, we're talking about the minimum value, not necessarily a point, but the value. And so that's going to occur at the vertex by whatever process you use to find the vertex. The y-coordinate of the vertex is negative 17. It does have a minimum as it is a parabola that opens upward. Number 2, find all the intercepts. Easy to find the y-intercept, substituting in a 0, f of 0. X-intercept, a little bit harder. You could use the quadratic formula. You're probably going to be more successful by completing the square. And the last one really has to do with the sketch itself, so make sure we have a good sketch. And then it's a little bit difficult as there's a couple different ways you can set up the sketch, and one leads to a better or more maximum area. So if we have our barn and we want two adjacent rectangles, we're going to go like this. So we would have x and x and x, and then y is that total length is probably the best way of approaching it. But any way you go about it, the best we can do is 7,500 square feet. Lesson 2.3, starting with long division. So we are going to divide 2x minus 4 into 6x squared plus 5x. This is a quadratic polynomial, and it is missing the x term. So that's going to be something in the inside the division here, the dividend. You have to make sure that if there's any missing terms, we include those. So we're going to write a plus 0x. It doesn't really matter with the divisor. It does matter in the dividend. So you can go, if you want to over here, you can do it, but it's most important in here. Because otherwise, when we go ahead and do everything, it's not going to line up in columns. We need an x squared column, an x column, and a constant column. So we're going to take a look at the first term here and the first term there. And you're going to ask yourself, what would you multiply the 2x by to get 6x squared? Just first term and first term. That would be 3x. Now, depending on how you've been taught this before, you might put it here. I just like to line them up. It does not really matter. We're now going to take the 3x and multiply by the entire divisor. So distribute that, stack it underneath. And then the key step for the long division of polynomials is we are going to subtract these. The most common mistake is, once we get past the first one, is to accidentally add. So we're going to go 6x squared minus 6x squared cancels. And if we chose this correctly, the first one is always going to cancel. Now we have to do 0x minus negative 12x, which turns into 0x plus 12x, not just adding. We don't get a negative 12x. You have to subtract them. We get a positive 12x, and at that time we're going to bring down just the one next term afterwards, just one next term, which would be the 5. Now we'll just do the process again. First term, first term. What do we multiply 2x by to get 12x? Positive 6. So we'll put a plus 6 up there. And again, distribute, stack it underneath, subtract, cancel. 5 minus negative 24 is positive 29, which is the remainder. And then the quotient, we're going to write that as a fraction. You have to have the sign. You absolutely must have a sign here. Otherwise, it indicates multiplication. So plus 29 over 2x minus 4, and and that would be our quotient. So here's our divisor. So if we kind of take a look at that, we have divided 6x squared plus 5 divided by 2x minus 4. And we got, initially here, the quotient of 3x plus 6. Didn't divide in evenly. Plus the remainder, divided by our divisor. So plus 29 divided by 2x minus 4. And that's essentially summarizing our process, just in terms of fraction bars indicating the division. But now if we fraction bust this, multiply everything by the LCD, which is 2x minus 4, let's take a look at that. We would get 6x squared plus 5 equals the divisor, multiplying everything by the 2x minus 4, 2x minus 4, times 3x plus 6, plus, and then if we multiply this by 2x minus 4, which would cancel out, we just get the plus 29. So essentially what this is going to be is, we're going to talk about remainder theorem and stuff like that, is for the division algorithm, it's writing our dividend as a product of the divisor and the quotient plus the remainder. This is the division algorithm. We just kind of illustrated at the very bottom there. We can write our function, the dividend function, as the product of the divisor function d of x times the quotient function, which is what we got by doing the division, plus the remainder polynomial. Okay? When you do it this way, you're not going to have this be a fraction at the end, unless the remainder is a fraction. And what they're saying here is, if there is no remainder, the remainder is 0, then we have found out that our divisor evenly divides into, or then is a factor of, the dividend. All right, checkpoint with long division. Just go ahead and divide our divisor, dividend by our divisor. Pause here. Don't forget to look for in the dividend any missing terms that have to be represented. All right, so as a quotient, here are all the steps. You should have gotten 3x squared minus 9x plus 25 minus 67 over x plus 3. If you had put plus and a negative here, that is also okay. And then what we're saying is, if we needed to use the division algorithm to essentially break up our dividend polynomial here, we would say it's equal to the divisor times the quotient plus the remainder. Divisor, quotient, remainder. All right. So possibly another option for us in the long division is to do synthetic division, and we are allowed to divide by, use synthetic division if our divisor is of the form x minus k. So x minus 2. Dividing by x minus 2, we can do synthetic. Dividing by x plus 7, we could do synthetic. If it was x squared plus 2, can't do synthetic. If it's 3x minus 5, can't do synthetic. It has to start with x and be linear that way. So they're kind of giving you the guidelines here. Probably not worth our time really to look at this from this way, but we're really going to understand it more with an example. All right, so use synthetic division to divide our dividend by our divisor. It does start with x and is linear here, so we can do synthetic. Now the key here, we got to go back, is we got to figure out what our k is. So x minus k, so x plus 2. So x minus what number gives us this expression? Think opposite. It's negative 2. Or if we set this equal to 0 and solve it, you're going to get the k that way. So if we go equals 0, solve for x, you get x equals negative 2. That's your k. It's really the 0 of the factor here, if it's a factor, or the divisor. So k is negative 2. The other thing we notice here, hey, it doesn't have an x term. And with synthetic, we're just going to list coefficients. So the negative 2 goes on the outside as our k. And then on the inside, we're just going to list coefficients, no variables. 1, negative 5. Ooh, there's a missing 0 here where there should be an x. 0 and 9. So that's how we set it up. Negative 2 on the outside, 1, negative 5, 0, and 9. We leave some room underneath, and underneath the 9, I'm going to kind of separate that off and show that my remainder is going to end up right there. All right. So here's our process. Whatever is the first number inside, coming from here as our leading coefficient, whatever it is, bring it all the way down under the line. Next, whatever comes underneath, we're going to multiply by the k. 1 times negative 2 stacks underneath the next number. So that would be negative 2. And here's where the synthetic process becomes a lot easier than the regular polynomial long division, because that one, a lot of mistakes made in forgetting to subtract and adding on accident. You don't have to worry about that here. We're just going to add straight down, make it very easy. So negative 5 plus negative 2 is negative 7. And then we just repeat the process. Take that number, multiply by your k, stack it under the next one. 14. Add straight down. 14. Multiply by k, stack it under the next one. Negative 28. Add straight down. The last one here, as we've sectioned this off, is our remainder, negative 19. So to write this, we're going to start here, kind of work backwards. Constant. So that's a 14. X, that's a negative 7x. X squared, a 1x squared. If there were more numbers, we just keep going. X cubed, x to the 4th, x to the 5th, and so on. So this represents 1x squared. Probably wouldn't write the 1. X squared minus 7x plus 14 with the remainder of negative 19. So if we were going to write it as the quotient minus 19 over our divisor. If we were going to use the division algorithm, we would say this is equal to this times this minus this. Remainder and factor theorem. So the remainder theorem, if a polynomial is divided by x minus k, then the remainder is the value of f of k. So what that's saying is we have multiple ways of evaluating a function at a number. For example, use the remainder theorem to evaluate our g of x for x equals 5. Now, if these were not the directions, we just plug in a 5. And that's probably a good way of checking your answer. But that cannot be your process when we're asked to use the remainder theorem. And the remainder theorem says, let's divide by x minus k. So we can divide by x minus 5. Now, as that is linear, and we essentially know our k value here, I would probably prefer to do this as a synthetic problem. Since this is not in this form, 5 is my k. So that's going to go on the outside. It doesn't look like I'm missing anything, so negative 2, positive 6, positive 1, negative 3. Go ahead and do it that way. So go ahead and pause the video here and see if you can work through with our synthetic division process. Let's see what you get. Remember, we should have brought down the -2, multiply that by the k, stack it, add straight down, multiply that by the k and stack it underneath, add straight down, multiply by the k, add straight down. So what we're saying is the remainder is the f of k, or in this case, g of 5. So we've just found out that g of 5 is -98. We did that by the remainder theorem. And you could check by just doing a direct substitution back into here to see. You might ask, it just seems easier to plug it in. And yes, that might be true, but you're going to see how this actually gives us something else in the future. The factor theorem, if f of k is 0, or if we tie that into the remainder theorem, if the remainder is 0, then your x minus k, your divisor, is a factor of the function. That's important information. Example number 6. Factoring a polynomial with repeated division. Show that x minus 2 and x plus 4 are factors. Well, the factor theorem says it's a factor if f of k equals 0. And the remainder theorem says if that's true, then the remainder was 0. So we should be able to divide these in, and that'll prove that we have factors. Because if we do the division and we get a 0 remainder, we've proved that each one happens to be a factor. So we're going to take this. We're going to divide by x minus 2. You could do it long division. I'm going to probably prefer to go synthetic. If I set this equal to 0 and solve, I'm going to get my k value. K is 2. So I'm going to divide in the 2. So go ahead and pause here for just a moment, see if you can get this, hoping, since we are trying to show, we know what we should get here as our remainder. We should get 0. So we have just shown that x minus 2 is a factor. Now I actually do not want to go back to the original. I want to keep working with this to show that this is also a factor, because I also have more stuff after that. I have to find the remaining factors. So I've just kind of made this a little bit smaller from a 4th degree. Now this is actually going to be constant x squared, x cubed, cubic. So I went down by a degree. I'm getting closer to finding all of the factors. So I'm going to use this. And now I'm going to divide by x plus 4. So synthetically, my k becomes -4. And the remainder is no longer there. So here's our constant right there. So it got a little shorter. Again, pause here, work out the synthetic division. We know what should happen here because we're trying to show that it's a factor. And again, it did work because we got a 0 remainder. And now what are we left with? Constant x squared. The remaining factors, we'll go ahead and write this as a polynomial and then factor it. 3x squared plus 4x plus 1. I don't know if you'll be able to see that. 3x squared plus 4x plus 1 is easily factorable. 3x plus 1 and x plus 1 are the remaining factors. Always pay attention to the directions because it might ask to write f of x fully factored, in which case we would write f of x equals this times this times this times this. Or another question might be, what are all of the zeros of f of x? 2, -4, -1/3, -1. So different ways of asking questions where you would go through the same process. All right, checkpoint, pause the video here to show that x plus 6 is a factor of h of x. Then, don't just find the remaining factors, show h of x in fully factored form. Your answer needs to be a function. Pause here. So we synthetically divide by k being negative 6. We got a 0 remainder, so we did show that it's a factor. And then to keep going, we're going to take 3x squared plus 4x minus 4, and that factors into 3x minus 2 and x plus 2. It doesn't really matter the order that we have our factors, 3x minus 2, x plus 6, x plus 2. Usually in the front I might have the one that has the higher leading coefficient for the x. That's it for today. We will see you next time.